In this video we're going to learn a little bit more about equivalence relations, and specifically we're going to prove a theorem that connects equivalence relations to set partitions. But since you don't yet know what a set partition is, that's where we're going to begin the lecture. So a partition, or a set partition, of a set X is a set of non-empty subsets of X, called the parts of the partition, which have the property that every element of X belongs to exactly one part. Now, like a lot of complicated definitions, this is a lot easier to understand when we see some examples. So let's begin just with a few example set partitions. So we'll start by thinking about the set of integers, and we're going to let O be the set of all odd integers. So 1, 3, 5, minus 47, and so on. And E will be the set of all even integers. Now, every integer is either even or odd, and no integer is both even and odd. So every single integer belongs to exactly one of the set O and the set E. And that means these two sets fulfill the condition for being a partition of the integers. So OE is a partition of Z, the set of integers. All right, let's take another example. So if we think now about real numbers, let's take the set of all strictly negative real numbers, written like this, and the set containing just 0 on its own, and the set of all strictly positive real numbers. Now, every single real number is strictly positive or strictly negative or 0. No real number is more than one of those two things. So these three sets here make up a partition of the set of real numbers. And we write the set of real numbers as R like this. Okay, and the next example comes from this picture which I've drawn up here on the right. I don't like that line. This illustrates a partition of the set X, which consists of the numbers 1, 2, 3, 4, 5, 6. And the parts which are supposed to be illustrated in this partition are 1, 2, 3. Those are the things in this circle here. And 4 and 5. And on its own, 6. Okay, so this is the meaning of a partition or a set partition. What we're now going to do is to prove that there is a connection between an equivalence relation on a set and a partition on that set. In fact, rather better than that, we're going to prove that equivalence relations and partitions are in some sense the same thing. To be precise, what we're going to do is, for every equivalence relation on a set X, we're going to produce a partition of that set X. And to every partition of a set X, we're going to produce an equivalence relation in such a way that these procedures are actually inverse to one another. So our first step is to show how to start with a partition and make an equivalence relation out of that partition. And the theorem which we will prove is this one here. If we take partition P of a set X, then the relation defined in the following way is an equivalence relation. And the way we define this equivalence relation is we define X to be related to Y, which we write with a tilde as usual, if and only if X and Y lie in the same part of P. So before we prove that this relation really is, in general, an equivalence relation, let's just try and understand it in the example which I showed you of a set partition from the previous slide. So here it is in the top right of the screen again. There's my set partition. Let's now explore what the relation defined as in this theorem would look like. So what it says is we define a relation by x is related to y, x tilde y, if and only if x and y lie in the same part of the partition. So here the partition consisted of the set containing 1, 2 and 3, the set containing 4 and 5, and the set just containing 6. So because 1 and 2 lie in the same part, we would have 1 is related to 2. And because 2 and 1 lie in the same part, we would have 2 would be related to 1. And similarly, 2 would be related to 3, 3 would be related to 2, 1 will be related to 3, 3 would be related to 1, and of course 1 will be related to 1, 2 will be related to 2, and 3 will be related to 3, because certainly 3 lies in the same part as 3. Okay, and also from this part of the partition, we would get the relations that 4 was related to 5, 5 was related to 4 because 4 and 5 lie in the same part, and 4 is related to 4, and 5 is related to 5. And lastly, looking at this part, we would get that 6 was related to 6. So that's the way in this construction of a relation from a partition would work in this particular example, which we saw on the last slide. So what I'm claiming is that this relation is in fact an equivalence relation. Now I've written at the bottom of the slide here the definition of an equivalence relation, which we saw a couple of lectures ago. You'll remember that an equivalence relation is one that has all three of the relation properties of reflexivity, symmetry and transitivity, R, S and T. So in order to prove this theorem, which we're now going to do, what we have to do is to verify that the three properties R, S and T hold for this relation. So we'll just do that one by one. We're going to do the reflexivity property, and there is the reflexivity property down at the bottom here. The reflexivity property is that every element is related to itself. But that's easy under this definition because it's clear if we take an element little x in big X, then it's obvious that x lies in the same part as itself. Well, it certainly lies in some part of the partition, because part of the definition of partition is that every element of big X lies in exactly one part. So certainly x lies in some part, and in fact it lies in the same part as x, right? This is really obvious. So x is related to x. Right, we've verified the reflexivity property. So let's now do symmetry. Okay, here is the symmetric property. The symmetric property is that if x is related to y, then y is related to x. But again, this is just obvious for our definition of the relation. If x and y lie in the same part, then certainly y and x lie in the same part. So if x and y are in the same part, then y and x are in the same part. I mean, looking at our example over here, 1 and 2 are in the same part, so 2 and 1 are in the same part as well. So if x is related to y, then y is related to x. And that means that the symmetry property holds for our relation. So finally, for the transitivity property, well, this time we have to think a little bit more. So again, let's just look back at the definition of transitivity for a relation. A relation is transitive if and only if x is related to y, and y is related to z, then x is related to z. So let's suppose x is related to y and y is related to z. Now if x is related to y, that means x and y lie in the same part of this partition. So let's give that part a name. X and y lie in their part. Let's call this part S. And if y is related to z, then y and z lie in a part. And we'll call this part T. Now I'd like x to be related to z. That's what we need to conclude in order to show that the transitivity property holds. But at the moment, x is in a part S and z is in a part T. So I'd better show that S is equal to T. But that's true because the definition of partition is that every element of the set capital X lies in exactly one part. Now y lies in the part S and y lies in the part T. So it must be that S equals T, otherwise the partition condition wouldn't hold. Okay, so we've established that S is the same as T. And now X and Z are both in S because S equals T. So X is related to Z. Okay, we have argued that if X is related to Y and Y is related to Z, then X is related to Z. So we've established the transitivity property holds. We've proved that this relation has the reflexive property R, the symmetric property S, and the transitivity property T. And so this relation is an equivalence relation, and that proves the theorem. All right, so we're done with this theorem. We've finished. And let's move on to working in the other direction. So now on this slide, what we're going to show is we're going to show how to make a partition from an equivalence relation. And the specific result we're going to prove is that if you have an equivalence relation written as tilde, as usual, on a set X, then the set of equivalence classes is a partition of capital X. So I've copied the relevant definitions at the bottom of the screen here. If you want to remind yourself of them, they're written at the bottom there. But now we have to prove this, this result for an arbitrary equivalence relation tilde. So we have to establish that the set of equivalence classes really are a partition. So let's do this. So the definition of a partition, remember, is that a partition of a set X is a set of non-empty subsets such that every element of the set X is a member of exactly one part. So it's very easy to see that the equivalence classes of an equivalence relation on a non-empty set, at least, are non-empty. So let's just add this hypothesis at the top here, non-empty. Okay, well, certainly equivalence classes are non-empty. As if you give me any equivalence class, so I'll write it like this, then it must actually contain little x. Okay, why is that? Can you see why it is? Pause the video and convince yourself why that's true. Okay, I'm sure you paused the video and did that. The reason is that, firstly, the definition of equivalence class at the bottom here is it's the set of all things which are related to x. So the equivalence class square brackets x is the set of all things which are related to x. And secondly, an equivalence relation is reflexive. So x is always related to x. And that means x lies in the equivalence class of x. Okay, so we've established that equivalence classes are non-empty. That's the first part of the definition of a partition. we now have to show that every element of big X lies in exactly one equivalence class. So in other words, what we have to prove is that if an element of big X lies in two equivalence classes, then actually those equivalence classes are equal. So let's write that down. We'll take x, little x, an element of big X, and suppose that X is in two equivalence classes, so the class of Y and the class of Z. So I could write that by saying X lies in the intersection of the class of Y and the class of Z. So what we have to do is actually show that class of Y equals the class of Z in this case. So let's be careful here. We can't possibly show that Y is equal to Z because we know from our congruence modulo n example that two equal equivalence classes can have different labels. So for example, we saw that under the equivalence relation of congruence mod 2, the equivalence class of 0 and the equivalence class of 2 were equal. So we can't possibly aim to show that Y equals Z, but what we can show, and we will show, is that the equivalence class of Y equals the equivalence class of Z. So we'll do that like we do very many equalities of sets by showing that firstly that the class of Y is a subset of the class of Z, and then that the class of Z is a subset of the class of Y. So we do this by showing class of Y is a subset of class of Z, and class of Z is a subset of the class of Y. Now actually, once we've done the first of those, the second one will work using exactly the same argument, so I won't repeat myself. I'll just say that the second one works similarly. So let's see how this argument's going to work. I've drawn a diagram at the top right here, which is going to explain how our argument's going to work. And what we'll do, in order to show that the class of Y is a subset of the class of Z, is we pick an element A in the class of Y. Now what we need to do is establish that actually A is also in the class of Z. And the diagram here explains how that works. So in the diagram, I draw an arrow from A to B like this if A is related to B. Now the fact that our relation is an equivalence relation means that it's symmetric. So if A is related to B, then B is related to A as well. So I might as well draw double-headed arrows like this, because if A is related to B, then also B is related to A. So in the diagram, the first thing we know is that A is an element of the equivalence class of Y, and we also know that X is an element of the equivalence class of Y. So that means X is related to Y, and I can draw this arrow here between Y and X. And I know that A is in the equivalence class of Y, so I can draw this arrow here between Y and A. And from that I get to do some deductions. I can deduce that A must be related to X because my relation is transitive. X is related to Y, Y is related to A, so I can go round in this triangle and I can deduce that actually X is related to A as well. But I also know that X is in the equivalence class of Z, right? That was one of our assumptions just here. If X is in the equivalence class of Z, then X is related to Z. So I've got this arrow here in my diagram. And now what have I got? A is related to X, X is related to Z. So again, by transitivity, I can complete the triangle and I get that A is related to Z. If A is related to Z, then A is in the equivalence class of Z, and that means A is an element, well, that means we've established that the equivalence class of Y is a subset of the equivalence class of Z, because we took an arbitrary element of the equivalence class of Y and proved that it was in the equivalence class of Z. So let's try and write this argument down. Now we've seen how it works in a picture, let's try and write it down. We chose an element A of the equivalence class of y. So what we get is A is related to y. We also know, because x is an element of the equivalence class of y, that x is related to y, and so by symmetry y is related to x. So by transitivity, A is related to x. Okay, A is related to y is related to x, so A is related to x. Alright, next step. I know that x is an element of the equivalence class of z. Now I have A is related to x is related to z, so by the transitivity property again, A is related to z. So we've shown that every element of the equivalence class of y is related to z, so class of y is contained in the class of z. Right, but the exact same argument with y and z swapped would show that z was the equivalence class of z was a subset of the equivalence class of y, so the equivalence classes of z and y are equal. Alright, we've now proved what we needed because we have shown that every element of the set capital X belongs to exactly one equivalence class, by showing that if an element belongs to two equivalence classes, then actually those equivalence classes are equal. That means we've completed our proof of our theorem.